Welcome to Spring Lib.
The relativistic kinetic energy is given by K is equal to mc squared divided by square root of 1 minus v squared divided by c squared minus mc squared. We can shrink this this equation into gamma minus 1 mc squared by writing a gamma is equal to 1 over 1 minus square root of v squared divided by c squared. Part A of the problem, using a non-relativistic we can write a kinetic energy for non-relativistic case, that is a 1 over 2 mv squared, or we can say the classical equation for kinetic energy, that is only equal to 1 over mv squared. We substitute the values for mass and v. 1.67 times 10 to the power minus 27 is kg is the mass of a proton times its speed, which is 8 times 10 to the power 7 meter per second. This gives us the non-relativistic kinetic energy to be 5.344 times 10 to the power minus 12 kg meter square per second square. Then for relativistic case, using the above equation that we wrote previously, we can write for relativistic case, we can write 1.67 times 10 to the power minus 27 times 3 times 10 to the power 8 squared divided by square root of 1 minus 8 times 10 to the power 7 divided by c square, which is 3 times 10 to the power 8 square, minus 1.67 times 10 to the power minus 27 times 3 times 10 to the power 8 square. Simplifying this, we get the kinetic energy, relativistic kinetic energy, to be 5.64 times 10 to the power minus 12 kg meter square per second square. If we take the ratio of relativistic kinetic energy to the non-relativistic kinetic energy, then we see 5.64 7 times 10 to the power minus 12 divided by 5.344 times 10 to the power minus 12. We get the ratio of 1.06. Then for a speed that is for the speed of a proton for a part B, that is v is equal to 2.85 times 10 to the power 8 meter, which is different than the previous problem, the speed. If we change the speed, then the non-relativistic kinetic energy, doing the same procedure, we get here to be 6.78 times 10 to the power minus 11 kg meter square per second square. Similarly, relativistic kinetic energy for this speed, we get here is 3.3 times 10 to the power minus 10 kg meter square per second square, which if we take the ratio of these values for relativistic to kinetic energy non-relativistic, we get here this ratio to be 4.88, which is higher than the previous problem. We understand from these results, which shows that the ratio of relativistic to non-relativistic kinetic energy, just as higher values in a higher speed when we approach the speed of light. But in low speeds, the ratio is too small that we can ignore it when we use Newton's law directly. So the summary is, for higher speeds, the ratio is greater, and for lower speeds, the ratio is lower, and therefore we can use the non-relativistic kinetic energy when we are dealing with Newton laws.